Good morning. So starting lecture 51. The last lecture at the end, I told you that the kind of model equations which are used in level 2 due to Mayer, of course, that is the interelectrode capacitances between gate and body or substrate, gate and source, and gate and drain for different regions of operation. And if you take all of them into account and plot the three capacitance against VGS, they look like this roughly. Here, of course, we are saying 0. It is not 0 for a small value to close to COX. Like so, with respect to COX, the variation of CB, CGS, and CGD against VGS are shown. Similarly, they depend on VDS also, as indicated by this equation. These equations were derived partly analytically and partly some simplification, introducing some simplifications which makes it more or less empirical in nature. This is so far as the capacitances between the gate and body, gate and source, and gate and drain. But then there are capacitances between the source and body, and source and drain and body. These are junction capacitances. Junction capacitances. The first one is CBS, the junction capacitance between the body or the substrate and the source. Between body and source. This is basically a junction capacitance, and that is given by expressions like this: Cj So these are the junction capacitances between the source and substrate, or source and body, and the drain and body, which are additional things which were not considered in the yesterday's or last lecture. And it is a very common model for simulating them. It's used almost universally. A simple way of simulating such junction capacitances. Here, if you remember correctly, then the kind of formula which you get is something like that. For a step junction, the capacitance is something like 1 minus V divided by VBI to the power half, 1/3, okay, like this. Half for 0.5, that is if MJ parameter is 0.5 usually for the state junction, whereas for the linear junction it is linearly graded junction, it is 1/3, and all these things I think you remember, which were discussed earlier. In simulating this, we have assumed the junctions looking like this. It is a simplified form of junction. Simplified form of junction. The first terms are due to the flat portion, the bottom layer. So the capacitance, you know that the junction which is formed has a more or less a flat region and then semicircular or cylindrical or elliptical region, but for simplicity it is being simulated like this. The sidewall regions are normally considered separately because of the high doping near the surface, which I told you earlier. The sidewall capacitance density is usually much higher than the normal flat bottom capacitance. So this Cj here, this Cj is nothing but the capacitance at zero bias when VBS or VBD is equal to 0 per unit area, per unit bottom area. That means this, assuming to be planar. So Cj is the capacitance of the junction at zero bias when CBS of CBD equal to 0 per unit area. Area means I mean the mask area. In fact, this area is nothing but the mask area. Please remember this. Through this mask, we are doing the diffusion or implantation. We assume that the bottom surface, which is assumed to be flat, has got the same area as the window through which the diffusion or implantation has been done. That is the approximation which is normally considered. Whereas CJSW is nothing but sidewall capacitance. SW stands for sidewall. Per unit perimeter. It is in terms of per unit length and it is per unit area. Please remember this. This, because actually it is a rectangular or region through which the doping has been done. So the perimeter is nothing but 2L plus 2W. For L by L I mean LS and LD. LS for length for the source, LD, WD, WS is the width for the source. So that way I can write AS is equal to LS into WS and AD is equal to LD into WD. Whereas this PS and PD values, they are the perimeters. This is the perimeter. The perimeter will be 2 into LS plus WS and PD will be 2 into LD plus WD. Phi j is the built-in potential of the junction. Phi j is a built-in potential or barrier. And is it okay? This is how, in doing so, we have introduced this coefficient, rather this exponent mj and mjsw. So what are the parameters involved here? Inputs to be provided. One of the geometrical input, ASAD, PSPD. Then this capacitance Cj, Cs, Gs, W, etc. you have to give the value, okay, and also you have to give the value for phi j and mj. Mj typically, as I have written earlier, Mj is equal to 0.5 for step junction and that is equal to 0.33 for linearly graded junction. Okay. Normally its value has to be chosen between the two. Step junction is one extreme side and linearly graded junction is the other extreme side. You have to choose a value between 0.33 and 0.5. You have to try to fit in with that. And phi j value for an N plus, because you note that this is an N plus P junction. In the case of N plus P junction, you can easily draw what will happen to this is a EF continuous at zero bias. In the N plus side, I can approximate Venn diagram like this. This is EC, this is EV. So this is the N plus side. And in the P side, which is the substrate, it will be something like this. So this will be the nature of the energy band diagram for the N plus P junction in equilibrium without any bias. So this is nothing but your phi j. The built-in potential. This is your intrinsic Fermi level. This is your so-called phi p, phi f or phi p. Here in these models we are calling it phi p. And this is your Eg by 2. Am I correct? This separation is Eg by 2, band gap by 2, and this is so you can easily find out that this is phi j can be modeled as phi Eg by 2 plus phi p. That means Eg by 2 plus Kt by Q into Na by Ni. ln of Na by Ni. That's how phi j is modeled. So here in simulating the values of CBS and CBD, so Mj and phi j values are to be taken from here, knowing the values of Na, Ni, etc., Eg, and an approximate value between 0.33 and 0.5, depending on the kind of junction which you have made. And of course, you have to give the values of Cj and Cjsw. You see clearly that the sidewalls have been considered separately because sidewall contribute in a very small device. It is a sidewall which dominates over the flat portion. It is a sidewall capacitance. In the modern technology, what we do, we replace it by an oxide. Then it is called oxide isolation. You remember, and that is done at the left of the source, at the right of the drain. Okay, to reduce the to improve the isolation between the components. There, of course, these equations have to be suitably modified. As I was indicating, but let me just slightly discuss it. In the last class, I was mentioning about it. If you consider the simple inverter, this is for the case of n-channel inverter. It could be a CMOS inverter, it could be N-channel inverters with different kinds of load, saturated, linear, depleted, and so on and so forth. And in all cases, for the complete analysis I mean the transient analysis. If the input voltage is a transient voltage, then you have to consider the way it is normally done. If I suppose I get a particular node here, any this node or any such node here, where a capacitance is there and a something so this is the device. In looking at this, it is nothing but the drain of this. Similarly, if I from this point, if I go up, there is another thing which is the source of the next device, the load, and a number of other capacitors maybe going to the different points. So for example, here we have a capacitance C, G, D, and here I have a capacitance which is C, G, S. This is CGD for the driver, and this is CGS for the load. So all these capacitances are there. Okay. Now, what will happen? I normally in nodal analysis, this is all in terms of voltages, isn't it? So the current in each component is equal to the voltage between the adjacent nodes divided by the reactance of the total impedance. Okay. So far as these devices are concerned, but the same thing, these devices, by this mean the resistive part I am saying. Between this and similarly there are, I am considering between this and so many points are there. I have not shown, yeah, this goes to normally ground as indicated here, and this goes to the so-called VI input, and this may be so-called VGS, VGG, like this. This goes to VDD. Am I correct? I have considered this particular node. I have considered this particular node. So at this node, which is nothing but the VO node, if I apply now the Kirchhoff's current law, which says the current from all the outward current or inward current from this particular node, the sum must be 0. Okay, and therefore, and these currents are expressed in terms of it is nothing but the difference between the adjacent node voltages divided by the impedance. So far as these two things are concerned, the currents here can be calculated from the model equations which I have already derived, which relates ID to VDS and VGS for the different regions. So these two currents are straightforward obtained from there in terms of B. And this current is nothing but the node voltage difference. So, and what is that? I C dVdt. C and rate of change of the voltage between the two. The capacitance of these two capacitors, which is CGD, CGD, etc., whatever may be, the inter-electrode capacitances, multiplied by the rate of change of the voltage between the adjacent nodes. Okay? And then you can find out, but there is a difficulty here is this, that all those four components which I have indicated here, they are non-linear components. Neither of them are independent of the voltage across them or the current passing through them. They are dependent on them. In ordinary circuit elements, these C's, R's, etc., they are independent of the voltage across them or the current passing through them. But here it is not so, and which makes the analysis extremely difficult. So what you have to do, as I have indicated earlier, you have to discretize in the time domain. You have to start with some trial variations which is obtained from DC analysis. If you change the input voltage from 0 to Vi, I know how all these voltages and currents change. And so this is, suppose it is a linear thing, slowly, as I am changing time from 0 to say 5 seconds or 100 seconds, then this is how. So if the time is very large, then I can assume the steady state things will go on. Suppose the input voltage variation is from 0 to 100 seconds or even 10 seconds. Then these voltages will follow that. Suppose it is a linear ramp. Input voltage varies linearly from 0 to Vi. Vi means it may be 5 volt if VDD is 5 volt. Okay, and suppose it takes place in 5 seconds or 10 seconds. In 10 seconds means very, very slow so far as these MOSFETs and other things. These are not normal switches. These are not mechanical switches. For 10 seconds is too long a time for them. So if I, therefore, for the 0 to 10 seconds, as you change, I know how with time different voltages and currents are changing. You start that as a trial and calculate the currents following that, okay, and obtain, read, after the first iteration, you obtain now the second set of voltages, because you need voltages to calculate the currents. You can very clearly see you need all node voltages for the calculation of the currents. Okay, now this is the first technique, that if you go on and you have to do in a discrete time domain. Now go on modifying it one after another, and gradually you have to, this is done initially for obtaining a trial things, because unless you have a good trial, the convergence will be an infinite procedure. To achieve to a particular value within a practical time limit becomes a very impractical thing unless your initial assumed value is not far from. If it is very far, then trial it, the kind of solutions it is, it takes a lot of time. Of course, there are many mathematical techniques today to reduce the convergence time, but it is the usual practice always that initial trial set should not be very, very different. And that has to be done by this kind of initial things, and of course, ultimately a time domain analysis has to be performed for this circuit, and this kind of things are very common in circuit analysis today. Circuit analysis techniques are very advanced techniques where voltage dependent current sources, current dependent voltage sources, or vice versa, everything is included. So it is not difficult now. These analytical techniques are better. And SPICE contains such very established techniques. So once you determine the DC values, the currents and voltage relationship, these are the DC values, please try to understand. The current, etc., through these things are nothing but from the DC analysis. And along with that, if you know the values of the capacitance, it is now possible to calculate first the DC analysis. To do the DC analysis, there the capacitors do not come into picture. Then you do the AC analysis under small signal condition, which is rather simple, as indicated earlier. In that case, times can be considered harmonic, so all DDTs, etc., can be replaced by j omega and all these things. A very typical technique. And the third is the large signal transient analysis, which is very important for the digital application, which is most complicated. And for that you cannot use any analytical approach. Just confirm. Mesh analysis finally gives a, maybe you are handling them in matrix form, the matrix manipulations you are doing, but otherwise it's basically an analytical kind of approach. This looping is not there. The iterations are not there. But when you are doing a numerical approach, you assume something, find out something, modify that, and go on do looping. And that's how you finally get to the trial value. That is done only in the case of the time domain analysis. That means in time, the transient analysis SPICE is the most difficult part from computation point of view, time consuming point. It is more time consuming than the other thing. DC analysis is very quick, and even the small signal AC analysis is also relatively quick. But transient analysis is rather time consuming. Okay. Now you have seen that after we discussed the level 1 and then we went to the level 2, we found that there are a lot of complications in level 2. So many things we did to achieve perfections, And as a result, we have introduced so many parameters which were not liked by the engineers. This was done by more or less from physics point of view. Engineers thought that using this way it is rather difficult, so they proposed, can we not do something intermediate? And that's how the level 3 approach came. Level 3, which was subsequently modified as Bisim, which I'll find time I'll discuss afterward. Level 3 tries to simplify the calculations, at the same time try to achieve more precision. And naturally, simplification means time of calculation, reducing the time of computation. So these are the three things. One is the whole thing should be much simpler and not as complex as level 2. At the same time, though it is simple, it must be quite precise, in fact more precise than level 2, because we have to use such models for micron or sub-micron kind of devices. Unfortunately, level 2 with a lot of efforts also, it could not go beyond 2-3 micron. Okay? So there, that means more empirical kind of things have to be done rather than pure physical things. And the whole thing has to be done in such a way that overall computation time is minimum. And for doing so, let us not go into the background how it was done. An equation like for the linear region in level 2 was obtained, or rather proposed, and that is main paper by Dang in 1979. This is the original paper, and thereafter it was modified. IDS is beta into VGS, VTH, this is the equation they consider. You just see the equation is rather simple, where FB is equal to gamma Fs So you see that here the whole thing, that the FB term is important. FB term contains two parameters, one is Fs, the other is Fn. Apart from gamma, which is already there, beta and gamma are nothing new. But Fs and Fn are nothing but the short channel and narrow channel parameters. Similar thing which we introduced earlier in the physics course. Fs is a short channel parameter. And Fn is a narrow channel. By narrow, I mean narrow width. And beta, as before, is a parameter which was defined earlier. It's a standard thing. So beta is equal to that mu. Mu is the mobility, cu is the oxide capacitance per unit area, w is the width, and L effective is the effective channel length. And this is the old thing. All right. Now this mobility mu is modified. This is the original thing, but mobility mu is modified in level 3 in the following fashion. Mu s. Instead of mu, you write now mu s. So beta is equal to actually mu s co x dashed. So mobility is modified to mu s. Mu s considers the vertical field effect through the following simple equation. Theta is a level 3 parameter associated with gate voltage and its typical value lies between 0.05 to zero point 0.1 per unit volt. Per volt. So instead of those complicated things, they use this simple equation for S. You know, it's called surface mobility. Mu is the bulk mobility, and you know surface mobility. Inversion carriers are all at the surface. The surface mobility is changed from the bulk mobility, and it is highly affected by the vertical field induced by the gate bias. It is simplified thing. Then the threshold voltage here is normally written like this, VFB here. VFB etc. is already defined and there is nothing special, but here you see that I have introduced a term sigma. It is a level 3 parameter. This is level 3 parameter which associated to the then induced barrier lowering. So I call it DIBL parameter. In fact, the short channel parameter, which I have already told about, short channel parameter, normally derived from the charge sharing model. You remember that? Short channel parameter, its value is less than 1. Normally derived from the charge sharing model, has been found to that it also gives you dependence on VDS, but it cannot explain that fully. In practice, if you do not use the sigma VDS term for the threshold voltage and calculate threshold voltage, you find a lot of discrepancy with experimental results. That means the charge sharing model, which determines the value of Fs, cannot fully explain the drain-induced barrier loading. And you will understand it very, if you remember the basic principle of charge sharing model, the so-called DIBL effect, which is a two-dimensional effect, was not considered there. But somehow the model is such the VDS automatically comes in. But that Fs value only cannot explain the total dependence on VDS, total dependence of VTH on VDS, and that is why this second term, this third term has been introduced, is a coefficient sigma attached to VDS, which explains the additional contribution due to DIBL. Then Fn, as indicated earlier, is a narrow width parameter. We have already written that. Narrow width, narrow channel parameter. Its value is more than 1, which I already told. Now sigma, there has been an attempt to model the value of sigma. Instead of arbitrarily choosing the value of sigma, some physical model of sigma was attempted, which looks like this. This is all based on some analytical derivations which we are omitting because of the lack of time. Analytical derivation gives sigma value, which is roughly something divided by COX dashed into L effective Q. That's something which is quite epsilon s and other things, that all constants coupled together for silicon gives a value like this. Okay, but in practice it was found that if you make theta exactly equal to 1, the tallying may not be that accurate, so they have kept a theta here. It's a fitting parameter. Once again, this value is to be adjusted slightly plus minus over and above 1. Okay, so sigma theta is another sigma parameter. Arbitrarily choosing sigma parameter is very difficult. Rather, we give an equation where we give another fitting parameter, but its value is very close to 1. So even if it is 1, this is more precise than arbitrarily assuming the value of sigma. So we are all discussing about level 3, please remember, level 3. The Fs value is given in level 3 as follows. Sorry. It's like this. When suppose if the source and drain both are grounded and grounded to the substrate, okay, so you have a profile like this as indicated here. This is the depletion layer boundary, and what they have done here, can you tell me what is WP and WC? Why the suffix they have chosen as P and C? WP, earlier I called it WS, WD, remember, but here in level 3 modeling, it is written as WP and WC. They have done something, and that is why they have used these suffixes. P stands for plane junction approximation, planar junction approximation. C stands for cylindrical junction approximation. In fact, because of the curvature here, the W, the depletion layer width is modified, and that is now considered in level 3. So they assume that in the plane portion of the junction, it is a planar junction approximation. WP value given by this is valid, is a simple plane junction approximation, of course step junction. Whereas WC, cylindrical junction approximation, it is a logarithmic kind of thing, and they have expanded and ultimately got a formula like this, and they use it for the simulating WC. You know, this is a cylindrical thing. You know that you have to write the equation, Poisson's equation, in cylindrical polar coordinates, and solve it. A Bessel function kind of solution will come. Sorry, a Bessel function kind of solution will come. After simplification, a series we get, and we keep terms up to the second order. That is their term. And so WC is approximated like this. So this formula, Fs for the short channel, appears to be perhaps is better than the one which was used earlier. Just a minute. Okay. And the Fn parameter, which I have already told you in the last lecture, it is the same thing, almost the same value they consider, given by where the delta value has been already told. The delta value. The delta is the value which has to be fitted, which has to be adjusted for obtaining this. Then for taking it, this is so-called WS, I have fully explained the model for the threshold voltage. Threshold voltage, all the terms have been explained. Now, the mu s, which is I have called the surface scattering mobility, surface mobility, also due to that does not consider the lateral field effect, the velocity saturation effect. Only the vertical field is considered. So that is also further modified, and I now call mobility as mu effective rather than mu. In that equation for ID, mu now becomes mu effective, which is given by mu s divided by 1 plus mu s VDS divided by that takes into account the velocity saturation effect, the lateral field dependence. It now, you know, the mu effective now depends on VDS. Earlier, the mu s was dependent only on VGS. Now VDS dependence has also been introduced. You know, the mobility will depend both on the vertical field and on the lateral field. Ultimately, therefore, In the equation where mu is there, in the current equation, it is now replaced by mu effective, which is given by this formula. Everything is known. Now, instead, VD sat calculation is not done in that complicated fashion here. Because it is from VD sat only you can calculate ID set. They do it in the following fashion. Don't think these will all come arbitrarily, they are based on derivations. That more or less completes the DC modeling of the level 3. So, remember how complex was the VT sat calculation in level 2. And then the inaccuracies with involving with Qi dash is equal to 0, etc. were considered. Level 2 is otherwise a physically very good model, but it is complicated. So, what they have done, they actually, what they do is, two things are done. One is that you have to have a set of very good experimental results for different channel lengths, doping profiles, etc., etc. So that